recall that we started looking at a beam splitter, and then we looked at what happens to a photon when it encounters a magnetic interferometer. So let me recall what we did was we had a 50% beam splitter generating a superposition of transmitted and reflected states. Then they are reflected by two mirrors and then recombined another beam splitter. So there are two inputs here, 1 and 2. This is 3 and 4. This is 5 and 6. So we calculated and showed that depending on the path length difference L1 minus L2, there can be photons can be coming out from port 5 or port 6 or both ports. The result is exactly the same as in classical interference, because in classical waves, if I had a single wave coming in from here, it splits into two parts, and then after traversing through two different lengths, comes back and interferes after transmitting and reflecting at the beam splitter. So if the phase difference between these two paths, depending on the phase difference, I can have constructive or destructive interference in both the arms. And quantum mechanically, this happens even for a single photon. So a single photon, which is incident on this beam splitter, actually splits into a superposition of these two paths, and then there is interference. And as I mentioned to you, this interference takes place irrespective of the size of this interferometer. Also note that if I had a detector here, then this detector will either detect the photon or it will not detect the photon. Because then you are looking at the particle aspect of light. Because either it detects a full photon or detects none. If you did not have a detector, you are looking at the wave aspect of light, because it goes through both arms and comes out from either 5 or 6. Now this interferometer is very interesting because tell you that I can use this interferometer to do what is called as interaction-free measurement. The question is it possible to get any knowledge of an object without knowing the presence of an object? Can I get knowledge of the presence of an object without knowing anything about the object before and without interacting with it? Okay, now there were two scientists from Israel who proposed a very interesting idea way back in '93, which led to what are called as interaction-free measurements. So the problem is the following. They just amplified the problem to make it more interesting and exciting. I have a large number of bombs. Some of them are duds because there is one sensor which is missing. And some of them are true bombs. The sensor is present. And the sensor is so sensitive that even if one photon hits that sensor, if it is a good bomb, it will explode. If it is a bad bomb, of course, nothing happens. And the sensor is such that if there is no sensor, I can send a photon through the bomb, across the bomb. And these are all closed systems, all identical. Can I find out even one bomb, which I know for sure is not a dud? Classically, the problem is the moment I have to observe. The moment I try to observe, it will explode if it is a good bomb. So, I can use this interferometer to do an experiment and give you a bomb which is 100% correct, good, and without exploding. The idea is the following. Imagine I set up this interferometer such that, as we had done, if L2 minus L1 is equal to 0, if I send a single photon from here, where does it appear? Only in 6, if L1 is equal to L2. Because this path and this path you can see are in phase, and this path will be out of phase by pi. So in this interferometer, if I set up this interferometer so that I send a single photon state from here, so I have an input state which is 1102, then the probability of getting a photon in 5 is 0, because output state is 0516. Now, suppose I place this bomb here. Okay, there is an opening on both sides, and I don't know whether inside there is a good bomb with a sensor which is active, or there is a dud in which a photon can get through. Now, if the bomb is a good bomb, it's not a dud. Okay, now, what happens? The photon comes in, it goes into superposition state. This bomb with a sensor is a detector, right? So, in a detector, if you put a detector here, the probability of detecting is half. And the probability that the photon is not detected here, that means it is in the other arm, is also half. So, if the photon, when the photon is in the superposition path, if this bomb is a dud, the photon can get through and this photon will arrive in 6. It is as if I have not put the bomb. If the bomb is not a dud, then this photon has a half chance of being detected by this bomb, in which case everything explodes and you lose the interferometer. Or the photon is in this arm and comes to the second beam splitter. Now the second beam splitter, what can happen? There is no other path for interference. So this has a half path probability of appearing in 5 and a half probability of appearing in 6. If you go back in the analysis and remove the second state, the ket 4 from that analysis, you will find that there is a half probability of the photon being detected in arm 5. So when I do the experiment, I send the first photon, it may be a dud bomb, so the photon arrives here. If the photon arrives here, I don't know. I know the bomb is a dud. Or it's a good bomb, but the photon has taken this path. I have no idea. I have no way of distinguishing between these two. If the bomb explodes, of course, everything is gone. But if the bomb does not explode and the photon arrives in 5, it means the bomb is a good bomb. Because you have destroyed interference, because it's like a detector here. Detector has not detected it. But because the photon has arrived in 5, it means there is an object in path 4. And because the photon has been detected in 5, it has not interacted with the object. Because if it had followed this path, it would have been absorbed by the object. The bomb is a magnification. I can have an object. I can have simply an object here. If I have an object here, if I set up the interferometer so that all photons incident in 1 arrive in 6, and if I put an object here, then, or in the experiment, suddenly I find photons arriving here, it only means that this arm or this arm, one of these arms is blocked by an object. And that photon that you have sent has not interacted with the object. Because if it had interacted, that bomb would have exploded.
So here we are destroying the interference effect to know what the path of the photon might be.
Yes. But please remember here, the photon has gone into a superposition path, but it has not been detected by the object. The fact that the photon arrives here means that the object has not detected the photon. The fact that the photon arrives here also implies there is an object in the other path, in one of the paths. So the photon has not interacted with the object, but I know there is an object there. So this is a kind of a result of an experiment which says that if the photon had gone along that path, it would have exploded the bomb. I get a result which is of a possibility. So these are called interaction-free measurements. Yes?
Can you tell this?
Okay. I have a photon incident from here. Let me take two cases. Okay, suppose I send a photon from here, and without this object, I will never find a photon arriving in 5. Now for this, please remember, it's not one photon I should send. I should keep on sending a number of photons every time I find all of them arriving here. Now, somebody does something in the experiment, and I see a photon arriving in 5. What would it imply? I have destroyed interference. That means in one of these arms, there is some object which has blocked this light. For example, here. Right? Now, so what I am saying is, the arrival of a photon in 5 implies the existence of an object in the arm, and the fact that the photon has arrived in 5 implies that the photon has not interacted with the object. Because if it had come along this path, the object would have absorbed it. The photon cannot arrive here if it had followed this path. So it has followed this path to arrive here, which means it knows the existence of an object in the other path. Yes, Prasoon?
Sir, this is with probability just 0.25.
Yeah, but there are more advanced versions of this where the probability can go to very high values. I can modify this. I don't have to choose 50% reflecting mirrors, beam splitters. I can choose different, and I can increase the probability significantly. So these are called interaction-free measurements, and maybe it can lead to applications where, for example, I may have an object in which I don't want to illuminate by even very little. I mean, for example, X-rays. I can actually detect presence of objects without having the X-ray at all interacting with the object. Things like this. There are very interesting consequences of this kind of an experiment, and so these are called interaction-free measurements, and this is a very interesting direction of research. And you see, quantum mechanics has within itself built a lot of interesting possibilities, and one of them which I thought would be interesting to tell you is this particular one, which is so what is actually happening is, what happens in this areas is, if you have information about the path the photon takes in the interferometer. No, I must modify. If there is information in the experiment which can lead me to the knowledge of the path of the photon in the interferometer, you will not observe interference effects. Please note, I may not access that information. If there is information in the experiment which can help me identify the path taken by the photon, then there is no interference. If there is partial information available to me, there is partial interference. If there is complete information available, there is complete destruction of interference. If there is no information available, there is perfect interference. Okay, so it's more to do with information rather than my act of observation disturbing the system. I don't have to even observe. The existence of information in the system can lead me to the to destruction of interference in the experiment.
Sir?
Yeah.
If I observe photons coming out of port 5,
yeah,
I have no way of knowing which path 3 or 4 has an object in it. So,
yeah, so I'm sort of saying that I put an object in 4, in the area of 4. In the bomb problem, for example, I put my bombs in 4.
True.
Otherwise, I have no way of identifying whether it is 3 or 4. But there is an object in this region.
But then I don't know what path the photon traveled.
I don't know. I don't need to know.
Then
no, so if I will say that in this region of volume, there is an object. I don't specify, I don't say it is in this region only. I can specify that in this entire region, there is an object. This could be a black box, right? There could be an entry here, and exit here, and exit here. All I will say is that initially all the photons were coming here, they were all coming out from here. Suddenly I see a photon here, that means in this volume there is an object.
I'm asking because you said that the reason why we are destroying interference is because we have some information about the path that the photon traveled.
Yes.
But I'm saying that we do not know what the path the photon took. We just observe it coming out of port 5.
No. For example, suppose let me assume that this mirror, one of the mirrors was wobbly. Okay. Then suppose now the presence of a wobbly mirror immediately tells me information about the path, because if the mirror wobbles when I send the single photon, I know it has taken this path. If the mirror does not wobble, it has gone through the other path. It's like a detector. It's what is called as a non-demolition experiment. I'm not killing the photon, but I'm still having the photon, but I observed the path of the photon. The moment I have a vibrating mirror in one of the arms, one can show that interference is gone. So it could be in this situation, what I'm trying to say is, for example, let me assume this is the polarizing beam filter. If it reflects horizontal polarization and transmits the vertical polarization, when they go through different paths, you will not observe interference, because two orthogonally polarized beams don't interfere. Now, why they don't interfere? Because if I measure the polarization state of the photon, and if I find horizontal, I know it has taken this path. If it is vertical, I know it has taken the other path. So that information is contained in the experiment. So the existence of information in the experiment destroys interference immediately. If I have partial information, partial destruction of interference. If I have full information, full destruction of interference. So I don't have to disturb the system. You see, many times we say in the electron microscope explanation, for example, you say that if you try to observe which hole the electron passes through, you scatter the photon from there and find out, etc. Those are all right, but there are also experiments in which I don't disturb the system at all. And the existence of information on the path of the photon will now destroy my interference, because you are not able to observe both the particle and wave aspects simultaneously at the same time. Okay, so there are more advanced versions of this experiment using multiple reflections and so on. So there are people who are very interested in this kinds of analysis, and with could be possibly a large number of applications. Okay, now what I want to do is I want to discuss something which is which I want to use a little later also for discussing. How do I detect light? Now, normally I have a photon detector. So what does the detector do? When light falls on it, the light gets absorbed and it creates electron hole pairs in a semiconductor, or it excites, it ionizes an atom, electron comes out, and the electron is accelerated, and I detect a current in the external circuit. So the basic process that is happening is ionization of an atom by the photon. So a photon detection process is something like a photoionization of an atom and detecting the electrons that are emitted by the ionized atom. Now there is an analysis which one can do. That means this is an interaction of light with atoms, calculating what is the probability of absorption, etc., which I will not go through. But what happens is the probability of photoionization at R position R and between time t and t plus dt is proportional to what is called as W1 R t dt, where W1 RT is expectation value of, I'll define this, E minus RT, E plus RT, where E RT is equal to E plus RT plus E minus RT, with E plus RT is I sigma square root of h cross omega L by 2 epsilon 0 V A L exponential minus I omega L T minus K L dot R. and E minus RT is equal to minus I sigma square root of h cross omega L by 2 epsilon 0 V AL dagger exponential I omega LT minus the total electric field operator is split into two parts, one having the destruction operator AL and the other having the creation operator AL dagger. The ALs are associated with exponential minus I omega t minus k dot r, and this plus implies essentially this is called the positive frequency part of the field. Although it is exponential minus I omega t, it's called the positive frequency, and E minus is the negative frequency component, and as you can see here, this is the Hermitian conjugate of this. E plus dagger is E minus. This is the probability of photoionization at a position r vector between times t and t plus dt that is proportional to this W1 of RT. Please note that it is not expectation value of E square. Intensity is proportional to the square of electric field. And intensity gives me the probability of detecting light at that point. The higher the intensity, the greater the probability of detection or photoionization. But this is an expectation value of product of E minus and E plus. Note that E plus contains destruction operators, E minus contains creation operators. So in this product here, all destruction operators are on the right side and all the creation operators are on the left side. All AL daggers will appear here and all ALs will appear here. And this particular way of ordering these operators is called normal ordering. The number operator, AL dagger AL, is a normally ordered operator. Number operator square is not normally ordered because it's A dagger A. So normal order would have been A dagger AA. So all destruction operators on the right and all creation operators on the left is normal ordering. And this is actually a normally ordered product of the two electric fields. This is the total electric field of the electromagnetic field operator. This is the positive frequency part, negative frequency part, and the probability of photoionization at any point r for a given state psi is given by this. Now this will become clearer as we look at some examples. So first let me start with the simplest example of a single photon multimode state. Single photon multimode state. Remember, we had written this as this summation over L. This is actually some expansion coefficients AL dagger 1, 0. Oh. We had already discussed this earlier. You can show that where n is the total number operator, which is sigma AL dagger AL. This is an eigenstate of the total number operator, which means the total number of photons in the state is exactly 1. This is not an eigenstate of the AL dagger AL operator, which means it has not well defined photon in the Lth mode, because that single photon is in a superposition of various modes. These modes could correspond to different frequencies, different propagation directions, different polarization states, whatever it is. This is also not an eigenstate of the Hamiltonian operator. If you calculate h psi, this will not be proportional to psi. Because this will be essentially sigma h cross omega AL dagger AL plus half. So this, if I call this L, this is M, CL 1L, 1M. So this will be equal to sigma CM this is h cross omega. AL dagger AL operating on this will give me AL dagger AL operating on 1M. If L is equal to M, it gives me 1. If L is not equal to M, it gives me 0. So this will be delta LM 1L plus CM will come there also, right? CM. So you see, this is not equal to, this is not proportional to psi. This is not an eigenstate of the Hamiltonian operator. This is not a well-defined energy state. Because this photon exists in multiple modes of propagation. So this is not an eigenstate of the H operator, but there is a single photon state. There is only one photon in the state because of this condition.
Omega L.
Omega L. Okay, now let's look at this. What is the probability of photoionization for this state? So this electric field. So I must calculate W1. Now let me take these states to be waves propagating in one direction, z direction, at the same and same polarization state. So the electric field operator, so instead of RT it will be ZT, because all of them are assumed to be propagating in the same direction. We'll have square root of h cross omega L by 2 epsilon 0 V AL exponential minus I omega LT minus KLZ. So K dot R I have replaced by KL times Z, and I am assuming scalar fields, which means all fields, all the modes are in the same polarization state. Otherwise, electric field operator is a vector operator. So I am assuming that all polarization states are parallel, all are polarized in one direction. So the total electric field is simply given by a scalar sum of all the components. So W1 of RT, to calculate this, so let me write here W1 of RT sigma CL star 1L. This is this part. Bra psi is sigma CL star 1L. Then I must multiply by EL minus EL plus, which is minus I M. Another index h cross omega M by 2 epsilon 0 V AM dagger exponential I omega MT minus KMZ into E plus, which is I sigma N square root of h cross omega N by 2 epsilon 0 V AN exponential minus I omega NT minus KNZ multiplied by sigma CS 1S. So this is bra psi, this is ket psi, this is E minus, and this is E plus operator. E minus operator, E plus operator, ket psi, bra psi. So now minus I into I is plus 1. Now let me operate this on the right and this on the left. So can you tell me, so sigma L, sigma M In fact, let me write all the sums here, sigma n and sigma s. There are 4 sigmas, sigma L, sigma m, sigma n, sigma s. Okay, so CL star, CS, I'll have h cross by 2 epsilon 0 v, square root of omega m, omega n. Now what happens when AM dagger operates on 1L? AM dagger operating on 1L. If M is not equal to L, it gives me 0. If M is equal to L, AM operating on 1L, ket L, huh? Delta ML into
L plus 2.
0. A dagger operating on ket increases, it's a creation operator, but A dagger operating on the bra will decrease. So there will be 0 L. Okay. Then this one. So I have the 2 exponentials which I have, right? AN operating on this. AN operating on 1S gives me delta NS 0S into exponential I omega m minus omega nt minus km minus kn there. It looks big, but it will get simplified very quickly. Just keep watching. Okay. So now I have delta ml. So this ml sum becomes a single sum, and delta ns. So this also becomes a single sum. So what do I get? Okay. So I will have sigma L, sigma n. So CL star, CS becomes CN, n is equal to S, h cross by 2 epsilon 0 v, root of omega L, omega n. Okay, now 0L, 0S. See, 0L means what? All are in vacuum state. Because when I write just 1L, it means that the Lth mode is in single photon state and all other modes are in vacuum state. So this means it's a complete vacuum state. This is a complete vacuum state. So this bracket is 1. So I will have exponential I omega, let me write omega, m becomes L, omega LT minus KLZ into exponential minus I omega nt minus KNZ. This is actually, sorry?
So there will be delta L.
No. This is 0L is a complete vacuum state. All, and this is 1. There is no SL because this is 0S. I'm just writing the subscript for the state in which has got destroyed. Okay. So this is sigma. Actually, this you see, this is nothing but Cn h cross omega n by 2 epsilon 0 v raised per half exponential I omega lt minus omega nt minus knz. C and CL star square of this, and then you have 2 exponentials which are complex conjugate. This is actually the mod square of this, which I can write as is per half exponential minus I kn. Now what is omega n by kn? Yes, c, the velocity of light in free space. independent of n. All modes are in free space. So omega n by kn is the velocity of light in free space. This tells me that the probability of detecting, please remember that when I discussed the single photon states, I said that I can have a multimode single photon state. It's like a wave packet. Depending on the CLs which I choose here, in writing this expression here, depending on the CLs which I choose here, I can have a state in which it's laterally confined, because depending on the frequencies which I add here, I can have a certain spectrum of frequencies which will lead to a wave packet of a finite duration. So this implies that this wave packet is moving at the velocity of c, because if the probability of finding the photoionization was maximum at this point at t is equal to 0, at some other time the photoionization probability will become maximum at this different point. It is as if this wave packet is moving in free space at a velocity c. This, I am only calculating the probability of photo detection. So if I create a multimode state like this, so and if the probability of photoionization is maximum at a certain time and will drop off on either side depending on the expansion coefficients I have chosen. So it's exactly like a wave packet. It's like a wave packet, but only consisting of a single photon. And this probability wave is actually moving like this in free space at a velocity of light c. And if it was here at this time t is equal to 0, it will be here at t is equal to, this is the probability wave. That means the maximum probability of finding the photon or the photoionization was here at t is equal to 0. At a later time it is here, at a later time it is here, later time it's here. So when we say when a single photon is incident on a Mach Zehnder interferometer, what we mean is actually it is this kind of a wave packet. It's not a single frequency state. Please remember, this is not a single frequency state. This contains, for confining the probability in the finite region of space, I need to add multiple frequencies. Exactly like in Fourier transform. It's a Fourier transform. If you take sinusoidal waves, they have infinite duration. To make a finite duration wave train, I must add many frequencies. I am doing exactly the same thing here. So if I put that single photon in a multimode superposition state of different frequencies, I will get a more localized wave packet, which will define the region of space in which the photon may be found, highest probability of finding this photon. It's like spontaneous emission. When the spontaneous emission comes out, it comes out in a single photon multimode wave packet. So when we say a single photon is incident on the Mach Zehnder interferometer, it's actually usually this kind of a, which is coming out from a spontaneous emission or parametric down conversion or whatever it is. The single photon wave packet comes and hits the wave interferometer, gets split into two parts and goes continuous. Yes?
So are we trying to interpret the probability of photoionization in terms of the presence of photon at that point?
I'm not saying the photon is there. I'm just saying the probability of photoionization. That's all I can say. Yeah.
No, that is fine.
So if the probability of photoionization goes like this is W1 for example, as a function of space for a given time, then I will say maximum probability is here. I'm not saying the photon was here.
No.
Yeah. So single photon wave packet defines me a longitudinal distance within which I will most probably find a photon.
So this gives the probability of photoionization. If this kind of multimode single photon state is incident on a beam splitter or a Mach Zehnder interferometer, so how can we say that it will have this kind of probability of distribution?
No. So if I take this and if I incident from here, okay, it's split into two parts. 50% probability. So if I put a detector here, if I launch at t is equal to 0, I will find this. Suppose I launch a single photon at t is equal to 0 from here. That means I have an atom here. Okay, spontaneously it emits at t is equal to 0. This photon then travels. I can tell you. So I have a detector here which is trying to detect the photon. I will detect it after a certain interval of time with a probability half. And over a duration, please remember. For example, if it takes a picosecond to arrive here, there's no point in waiting for a nanosecond because the photon must have gone to the other side anyway. So I know, if I know this distance and if I know the duration of the photon wave packet, I know when I am expecting to detect the photon here.
So, over a duration means the variance in the time of detection.
Yes, depends on the wave packet duration. Yes, if the wave packet is much longer, then yes. Now please note that this is related to the coherence time. It's all interrelated. Yes. So I can actually, when we do an experiment with Mach-Zehnder, and I say when a single photon is incident, it is essentially stating that a single photon wave packet comes and splits into two halves and then continues and interferes. Of course, please note that the path difference should not become much longer than the spatial extent of the wave packet. Then there will be no interference because they will arrive at different times on the outward beam splitter. And that is exactly your conditions for interference when you do a classical interferometer and make sure that the path difference is less than the coherence length. It's the same thing in a quantum fashion. Sorry?
If the path of the arms is less than the coherence length,
then there will be interference. Because then they will arrive simultaneously almost. If the path length difference is much larger than coherence length,
obviously they will not be in phase. I mean, the phase cannot be maintained.
In classical. But what it means that the probability, these two will not arrive at the same time at the beam splitter and they will not interfere. Then you will have finite possibility of detecting the photon here as well as here. Okay. Okay, so we'll stop here.